So what we're talking about today is Fourier series, which I think you've maybe seen a little bit in a lecture with Dr. Bennett in one of his videos. But what's cool about Fourier series is you can take a function and write it in terms of an infinite series of sine functions, which may not seem great, but actually has many applications. So it ends up being a pretty cool thing that you can do, and is essential in some areas of engineering and science. It's just kind of a neat thing mathematically anyway. So what's the basic idea? I've got a little itinerary here, but I'm just going to pull from it. So let's take this definition and start looking at it. So we can define a Fourier sine series in the following manner. So there are Fourier cosine series, there are Fourier series that are combinations of sine and cosine, but this is going to be a Fourier, it looks like Fourier, but it's a Fourier, pronounced Fourier, sine series, so called because the terms all involve sines here. And if we look at this, we try to see what's going on. You've got a series of terms where each of those terms are some coefficient times a sine function. It's not always the same sine function. It changes depending on the index. Notice there's a n here, an n here, and an n here. So each different term looks a little different in terms of the sine function. To kind of write out a few terms, what this would look like is b sub 1 sine of 1 times pi x, or just pi x, plus b sub 2 sine of 2 pi times x, plus b sub 3 sine 3 pi x, and so on. I don't know about you, but I usually like to just kind of see what the series looks like expanded a little bit. Kind of helps me get a grip on it. So we see each sine term is a little different, just shifted with a different frequency times its index, which will, I think, will be something that you can absorb a little more deeply once you see later what happens when you add more and more terms. That when I just said the frequency changes, that's actually a pretty critical property here. But if you look at this, the only thing that could change from one function to another, so if you, let's say, wrote another function g of x, and instead called this one, let's say, c sub n times sine n pi x, the only thing that can be different between these series are these coefficients here. So these coefficients completely determine what this function is. So it's really worth noting. I'm going to erase the g function. This was just an example of having some different function. But in general, your b sub n's totally determine the function. And that's really important. So b sub n's totally determine f of x, or f in general. All right. Now, what are some facts about a Fourier series of this nature? Well, one set of facts is if we take f of 0 and we take f of 1, we can compute those without too much trouble. And I'm kind of curious if you see what they are. So if you would just say in chat if you are able to quickly compute or just see what f of 0 would be by substituting in for x over here, and the same thing with 1. So if you substitute in 1, what would you get with this series? Okay, good. Thank you for those who gave some feedback. In fact, they are both 0. Oops. So we have 0 here and 0 here. So you can think of these as boundary conditions in the same way that we've been looking at boundary conditions for differential equations so far. Boundary conditions for boundary value problems. What we'll be doing is we'll be looking on the interval 0 to 1 And then we'll be kind of looking at what happens to functions and their corresponding Fourier series or Fourier series that would match up with them on that interval. So the reason that we care about this end behavior, this end behavior, is that we're going to look on the interval from 0 to 1. And we're going to kind of think what happens in this interval. We know that if we have a function f and it is written as a Fourier sine series, we know that in that case, what's going to happen is we're going to cross the x-axis at x is equal to 0 and 1, and then it's going to kind of do whatever in the middle here. All right, that's good to know. Now, it so happens that there's a fact that will let us determine or compute what the bn's are. So like was mentioned here, these bn's totally decide what's going on with the function f. So it'd be nice to have a way to figure out what are those bn's. That is, if we had a function, let's say f of x is equal to e to the x, so we would like to know how to find the bn's. For example, if you had e to the x, you'd like to know e to the x is b1 sine of pi x plus b2 sine of 2 pi x, etc., plus b3 sine of 3 pi x, and so on. But what are these b1, b2, b3s? We can find out what they are, then we're in good shape. Then we can write the Fourier series for a given function, such as e to x or whatever other function we'd like to know. Okay, so let's look at a few other things that will help us. It's also a fact, and you can get this. This is not something out of your reach. You 100% can do this just using some basic, some basic integration techniques from Calc 2. So if you were to take the integral from 0 to 1, and we care about the interval from 0 to 1 because of the end behavior we just looked at. If you look at the integral from 0 to 1 of the following, sine of n pi x, where n is just some positive integer, and then you multiply that by sine of k pi x, where k is also some positive integer, and you integrate that with respect to x, you're going to have one of two things. Either you'll have 0, or you will have 1/2. And what's nice about this is that you have 0 in all cases when k is not equal to n, except when it is equal to n, you have 1/2. So you have 0 almost always, with only one time when it's not 0, and then it's 1/2. Now that may seem a little, what's the word? A little contrived, or maybe not. It might not be clear why it's necessarily useful immediately. But we can use this fact to find out what the bn's should be. Remember, if I flip back, we really want to be able to determine what the bn's are, because if we do that, we can totally determine how to represent the function or a given function that we care about in terms of a Fourier series. If we have a sine Fourier series, then like this, nothing's ever going to change with the sine pi n pi x. That's always the same. The only thing that could be different between the different functions is what these b sub n's are. So they totally determine our function f. This fact will allow us to figure out what they are, which is very nice, very helpful. Otherwise, I don't know that this would be a helpful thing if we couldn't compute the bn's. So let's look at how we would do this. If we take the integral from 0 to 1 of, not sine, of f of x times sine k pi x with respect to x. I'm going to highlight this f of x in another color. I would like you to take a guess in the general sense, just so it's not like just me talking at you only, because that's, you only learn when you're sort of more actively engaged. What could I replace this f of x with? So what do we know about f of x, or what have we been saying about f of x? We can write it another way. Would you just say in chat what you think we could do? You don't have to be super specific, but just what's something I could put in place of f of x? So what could I put here instead? And again, don't worry about the details of exactly, what I should write, but more just in general. What could go there? What is a way we have represented f besides just writing literally f of x? We wrote it another way. Yeah, and again, don't worry about the details. So I see some people are seeing what I'm talking about here. If not, that's okay. That's okay. I'm being a little vague. But what we want to do, okay, so thank you for those who gave some feedback. What we want to do is write this as the Fourier series that we saw from before. So if I jump back, we've seen f of x can be written as this here. So instead of writing f of x, what we can do is write this series. Okay, so let's do that. In fact, I'm going to even just copy this and put it here. I'm going to color it also yellow to kind of visually highlight the fact that it is just f of x. It's just another way of writing it. So we just replaced f of x here with its Fourier series. All right, now I'm going to do the following thing, which may or may not be okay. And I'd like you to tell me if you think it is okay or is not. Long story short, I'm quote unquote pulling out the summation outside the integral. Is that okay? What do you think? Yay, nay? I said sun. I mean, I do like the sun, but it should be sine. Praise the sun. And if you think this is okay, why would this be okay? If you don't think it's okay, why would it not be okay? And as usual, I'm happy to hear from everyone. So even if the answer is I really have no idea, that in of itself is also helpful, just to know, where people are at. Okay, this seems to be giving people a little more trouble. In fact, you can do this, which I totally understand if it's giving you trouble. Like, it's not something that we use a lot of, right? So it's not something you've had a lot of practice with. I think you would have maybe seen it in Calc 2 and then probably not done a lot with it. In fact, you can. There are some conditions to be able to do this. You can't always just automatically do it. There need to be certain conditions like continuity of the functions and so on. I've even forgot what the conditions are like exactly, but in this particular case, we can do this. But just note that there is something to check. It's not just like an automatic thing. You do need some nice conditions to be able to do it. So just a note that we need quote unquote nice conditions, which is actually a semi-formal way of saying that mathematicians use to just say there are certain things you have to satisfy, but we either don't want to bother to state them or we don't remember at the moment. So there is something that needs to be satisfied there. Now, this one I am 100% sure you'll be able to say whether this is okay or not. I have no doubt that everyone can say this either is okay or it's not okay. So I'm curious in chat if you'd tell me what you think. Is this okay or is this not okay? And again, why? Why or why not? Okay, good. For those who gave some feedback, especially those who gave some description of what you're thinking, why it is or is not okay, I appreciate it. I think we pretty much agree all that it is okay. Some justifications for why it's okay are because Bn is a constant when compared to what we're integrating with respect to. That is, I mean, one, it's a constant like period, but even kind of more broadly, it does not involve x. So any factors that don't involve x, you can pull out because there is no change that the integral sees. The integral only looks at change in terms of x. So if there's no x there, there's no change. So it doesn't need to be in the integral. So indeed, we can pull out b sub n. We could not pull out, let's say, sine n pi x, for instance. That we couldn't because that has an x. The integral sees that as changing, so it needs to stay in the integral if it's seeing it as changing. But now we have this series, and what I'm going to do is I'm going to put some brackets around here to really show that you can think of this as being a series of integrals, definite integrals. So they're actually numbers, once you actually go through the computation, but it's a series of these nonetheless. Now, at this point, I know you can make this next step. It may be just a question of kind of how fast and so on, but can you see what this entire series simplifies down to? And when I say that, I say, consider this and look how that is exactly this and how that tells you you're going to have either zeros or 1/2. So using that notion, this with the fact above, you can totally decide what, or like figure out what the series is going to be, the whole series, whole thing. So in the next step, we don't even need to write a series. What does this whole thing simplify down to using this fact? It's not like one super obvious. You have to compute and just think for a second or two, but I mean, more than a second or two, but there's a little bit of mental or paper computation to do. So I'll give you another couple seconds to see if it happens to pop out at you. If not, it's okay. No pressure. Okay. This again is also seem to be a little bit tougher, which is all right. I didn't necessarily think it would be super easy. If you take and use the fact here from above, each one of these, you're going to get either 0 or you're going to get 1/2. That's because up here, you either get 0 or you get 1/2. You get 0 almost always. So in every case where k is not equal to n, you get 0. So that means, as far as the series is concerned, the only place you're not going to get 0 is with exactly one term. Notice the n is the thing that's changing. The k is not changing. So what that means is that the k is fixed, the n keeps changing, and as long as that n is not equal to k at 0, but at some point it hits like the same level as k and ends up equaling k. And in that case, what this whole thing becomes is just 1/2. So what you get is a single term that's non-zero in the series, and it ends up being bn times 1/2. I'm sorry, actually bk, because it's where k is equal to n, is the only non-zero term. All right, so you have bk, which I'm going to write just to look a little nicer. You have bk times 1/2 is equal to this integral. Seems fine. Let me shrink this, resize, shrink it, and raise this up. What that then means is you can take bk, multiply both sides by 2, and you get bk is equal to 2 times the integral 0 to 1 f of x sine k pi x dx. Okay, so is this good? I claim it is good. And actually, I'm going to make that claim and see if you can justify. Like, hopefully, I've gotten you in the habit of maybe doing what you already do. And when we do something, ask like, who cares? Like, what's the point? And that's what I'm asking now is, what was the point of this? Why are we doing it? It's not just to like move stuff around for fun. There's something useful in finding this. What do you think is useful in finding this? What are your thoughts? I'd like to hear from you. And if the answer is no clue, then that just means I've done a bad job of setting this up, which is on me, not on you. Okay, I just saw a few not sure's in chat, and pretty much that's it. So I'm going to assume that everyone else is also not sure. Well, what did I start out by saying here? That the B ends, they totally determine F, right? That the only thing that's going to change between the different Fourier series, and it's not going to be the signs. Those are always the same. That's the same in a Fourier sine series. The only thing that changes is the B sub n's. That means in order to figure out what's going on with the series, we just need to know what the B sub n's are, because everything else is set. We know it's going to be a series. We know, it's going to be, in this case, a sine Fourier series. And there's an exact certain format to it. So the only thing that could be different between the different series is B sub n. That's the only thing that can change. So we want to know what they are. For example, if we wanted to write e to the x as being equal to a Fourier sine series like this, we know exactly what to write with the sine parts, but we don't know what to write with the coefficients. So the coefficients, they determine the function. And they determine what the series will look like. They're everything. We really want to know what they are. So over here, what have we done? We've used the fact that you could, just fine by taking integration by parts. I think probably twice in this case, but just using some basic integration techniques. We can now write that bk is equal to this. So we wanted to know what the b ends are. Now we can find out what they are. It's k here, but it's the same if we replace the k with n's. So we wanted to know what these coefficients are. Now we have a formula for them. They're equal to 2 times this integral, where this integral is whatever actually our function was times sine. So if we could figure this out, like this integral, if we could compute it, then we could compute the b sub k. As an example, let's say that we wanted to write the function f of x is equal to 5 as a Fourier sine series. Now, 5 is pretty simple as a function. So we're only doing this to kind of get a sense of how you would write a function as a Fourier sine series. It is not going to be necessarily super helpful to us or like to people in general. It's just more practice of doing it just to see how you might, because 5 is relatively simple. So let's see how we might do it. To find the nth or kth coefficient, that's going to be the twice the function, which is 5 in this case. Actually, I'm going to even write f of x to really emphasize the point, times sine of n pi x dx. So here's the function. It's going to be 5, but it could be whatever function. It'd be a different computation if it was a different function, but same idea. And this will end up being pretty simple because it is just a constant. So we can factor out the 5, we get 10. Now we have a really basic integral to solve, or an antiderivative to find. So we get 10 times n pi negative cosine n pi x, evaluated from 0 to 1. Or written another way, we can write that as cosine of 0 minus cosine of n pi. Written yet another way is 1 minus cosine of n pi times 10 times n pi. And now this value, b sub n, will depend on whether n is even or odd. So if n is even, we get cosine of n pi is equal to 1. So b sub n is equal to 0. If n is odd, cosine of n pi is equal to negative 1. So b sub n is equal to 20 over n pi. So the big idea here is that we wanted to represent functions as Fourier sine series. In order to do that, we needed to find the b sub n's. To do that, we used a fact about products of sines, the integrals of products of sines on the interval 0 to 1. That gave us a formula for what the bn's should be. We use that formula in this case to find out what the bn's should be. And now for the function f of x is equal to 5, we can actually write what the Fourier series is. So we can say that 5 is equal to f of x, which is equal to this series of b sub n sine of n pi x. And now we know what the b sub n's are. Actually, I can't write a nice a nice formula for them because they alternate between 0 and something else, but I can write out the terms expanded. This would look like, actually, let me write it expanded anyways. Pi x sine 2 pi x plus b3 sine 3 pi x plus etc. And now, just very simply, just to make sure any of this is, sticking to the wall, as it were, tell me what is B1, B2, and B3. Would you just write in chat, what is B1, B2, and B3 in this case, based on the work we've done? And do remember that we do know the n. This first term is n is equal to 1. The second term is n is equal to 2. Third term is n is equal to 3. And for those of you who have put something in chat, thank you for your feedback. I appreciate it. So if we just use this formula, we have that Bn is 20 over n pi. The n in this first case is 1, and 1 is clearly odd. So we have 20 over pi times sine of pi times x plus 0. Okay, I'm back. For some reason, I got dropped. I don't know why that's the case. Let's see. I think maybe Emma got... Okay, other people crashed too? Yeah, mine certainly did. But let's get this back up here. Here we go. Okay, so we have 0 for B2 because 2 n is equal to 2, that's even. And we have plus 20 over 3 times pi, which can be easy to miss, times sine of 3 pi x, which in some ways should be absolutely ludicrous. That you can take any given x, let's say x is equal to 1/2, substitute it in here, and what you get out is 5 in the end. That just seems crazy. To me, at least. I don't know. It seems cool. Infinite series is really neat like that. But this would be an example of doing this with a function where we take a function and then we write it in terms of its Fourier series. Let me spotlight this video. So that would be how this works. Okay, now let's finally get to the applet here. Now that we have some sense of kind of what's going on. So if I end the share here, or switch the share to this one, there's 2 applets. The first applet has to deal with the questions 1 through 5. And then once you look at 6 and 7, then you'll switch to the second applet. The difference between the two is the first applet has a single function, like shown up above here. And then the other one has 2 different functions that can be sort of split. So you can have essentially a piecewise defined function where you have one function up until x is equal to 1/2, and then after that, you have a different function. But the first one is just 1. I'm actually going to reset it to what I think it was before. Yeah, there we go. Okay, so what are the elements of this? In red is going to be y is equal to f of x. That is, we have just a cubic, in this case, we'll look at a cubic polynomial. That's the curve in red. In blue, what we have is the partial Fourier series. So in blue is the partial Fourier sine series, or sine Fourier series. I'm not sure if you say Fourier or sine first, but either way. And I say it's partial because you only have a certain number of terms. In particular, that number of terms is decided by what is put here. So that's the limited number of terms. If you were to write, let's say, one term, what that would look like is the following. You would have one term would be just b sub 1, nothing fancy, times sine of pi times x, or 1 times pi times x. If you had 2 terms, it would then be b sub 1 times sine of pi x, the same as we had with one term, and then you add another one, b2 sine of 2 pi x. So on and so forth. I'll write one more. It may not appear yet, but it should appear soon. Actually, I'm going to copy this and just add one. Plus 3, or no, b3 sine 3 pi times x. All right, and here we are. Good. So one term, you just have just the first term of the series. With 2 terms, you've got the first 2 terms of the series, and so on and so forth. So that's what the limited number of terms means. So for instance, if I change the number of terms, we should get different blue curves. So if I change it to 2 and then update the graph, we get a new blue curve that's now given by the function with 2 terms. We change it to 3, we get another blue curve that's now based on the 3 terms, and so on. And you can go up to 200 something, 250 roughly. If we do 100 terms, notice, and then we clear the old curves, notice how close this blue one is to the red curve. Now, these are related based on what we just looked at with the Blackboard iPad writing. These are related in the following way. Remember that these coefficients, B1, B2, B3, in general, B sub n is determined by taking the integral from 0 up to 1 of f of x. Actually, I'm going to leave a space for f of x just to highlight the fact that that's going to be in red. And then multiplied by sine n pi x dx. So it looks like this. And now let me add a part in red. Yeah, there we go. That works out well. So in order to find these things, you actually need the function f of x. But what's interesting is as you take many, many terms, it seems like you kind of get something like the blue curve, the Fourier sine curve, starts to line up really close with the actual function itself, which is nice. In theory, with an infinite number of terms, it would exactly line up. They would be exactly the same thing. Computers have trouble with infinity for obvious reasons. But nonetheless, that's the idea, that as you take more and more terms, you get kind of closer. Or in theory, maybe that won't always be the case. So this is the setup for what you would need looking at questions. Sorry, it's going to look a little messy, but for questions 1, 2, 3, 4, and 5. Then once you get to 6 and 7, what you want to look at there is now having, can I move this? You have the same thing. Notice, yeah, all this is going to be the same. Where your red is, actually, let me even highlight that. The red is given by these here. Like that's the red. The blue is given like so. So you're comparing the red actual function to the partial Fourier sine series. And if I jump back to the other applet, and maybe I go back for a second to just the one, clear this. This function, since it's a cubic, it's going to be equal, or it's going to be, continuous on the interval 0 to 1. With the second applet, what you're exploring is how things can be discontinuous, or in the first case, like how it's initially set up when you open it. You could have a corner here, so where they meet, but there is no derivative. So like the corner you explored in Calc 1. You have a corner, or even just as I showed here, you could have a break. You could just say it's going to be 2, and then it's going to jump down here to this function. And what's interesting is to explore what happens with the Fourier series when your function, which is in this case no longer a cubic polynomial, oops, or I should say cubic polynomial piecewise defined, maybe. So when you have a discontinuity here, what happens with the Fourier series? So for example, if we look at, let's say, 10 terms of the Fourier series, it kind of does this thing. If we look at 2, yeah, it's not that great at lining up. But once you look at 10, it starts to do kind of this really interesting thing where it starts to wiggle more, quote unquote wiggle, but it starts to kind of look maybe a little more like the graph. If you go up to, let's say, 100, now all of a sudden, clear the old curves, it's actually looking pretty darn close. Kind of at the ends of each of these, you have more drastic amplitudes and wiggles, but it's really starting to line up quite a bit more, which is kind of fascinating, at least to me. And you can take this, like I said, up to 250-ish terms. It says in the lab. Yeah, so that's essentially what you're doing is you're exploring the behavior of the Fourier series as you add more terms and how it compares to your functions in red. And I think that's all I've got for you as far as things I wanted to present and just information to convey. I hope this has been somewhat helpful in trying to better understand this. I will post these videos later, but stick around if you've got any questions you want to ask. But otherwise, you have a good day.